Today I'd like to talk about voltage versus current. Now again, I'm going to be using a very oversimplified explanation here to try to get my point across. So what I did is I googled a basic explanation of voltage and current, and this is what I got. So this is what somebody thinks is an introductory and basic explanation. And again, this really reminds me of why I'm doing this video series on trying to make this very simple to understand, because again, somebody else thinks this is simple. 1 volt is the potential difference between 2 points where 1 joule of energy is used to move 1 coulomb of charge from one point to another. V equals J over Q. And if you're anything like me, you're probably looking at that and you know just as much after reading it as you did before you read it. So let me try to explain this in a manner where it will make sense to you if you don't have a formal education. There's voltage, which is measured in volts, and there's current, which is measured in amps. What's the difference between them? Well, voltage is the potential difference, whereas current, or amps, is the actual amount of power. That still probably doesn't make sense, so let me try to explain it with a really kind of silly analogy. Let's say I'm running at 25 miles an hour and I hit you, but I'm weak. I'm just a person. I can't really do much damage. So if I run into you at 25 miles an hour, I'll hurt you, but you don't really have to go to the hospital. Let's say I'm sitting in a car. A car is really heavy. A car can be 1 or 2 tons. Let's say I'm driving my car at 3 miles per hour. Even if I'm driving the car at 3 miles per hour, if the wheel goes over you and runs you over and goes over your whole body, you're probably going to be dead. There's a really good chance that I'm going to kill you. So even though the speed is very low, I'm still transmitting much more energy. So think of it like this. Me running into you is like 25 volts at 1 amp, whereas the car running over you is 3 volts, but at 1,000 amps. So the way that you get watts, which is power, is a mixture of voltage and amperage and resistance. So how much resistance is there in the circuit versus how much voltage and current there is. So when you think of that in that way, hopefully it makes it a little bit easier for you to get an idea of what voltage and current are. Now obviously if you want to transfer high amounts of power, it makes sense to run your circuit at a higher voltage, because for any given circuit, for any given resistance, for any given type of load on a circuit, the higher voltage will be able to transfer more current, and the current is the energy that's moving through it, and that's really that. Now I just mentioned something that's a little confusing, which is resistance or impedance of a circuit. So I was talking about how voltage and current relate to power. I was saying that for any given voltage, the circuit's resistance is going to set how much current can go through. So the current is the actual power. The current is the energy that's moving through the circuit. Now you don't set the current. You never set the current. You can't tell how much current is. You can't just say, here, send this much current to the circuit. What you do is you put, let's say, 12 volts into the circuit, and the amount of current that's going to move through is based on the resistance, also known as sometimes the impedance of the circuit. So what do I mean by that? Well, let me go back to the screen over here, and I'm going to show you what I'm talking about. Now I want you to think back to that video that I just recently did where I was talking about how the 5 volts doesn't really want to be 5 volts, but the way we get it to do anything is by putting ground on the other side of a chip. So remember when I said that 5 volts is going to this chip, and what this chip is saying is, yeah, we'll let you get to ground, but first you got to do all this shit first. You have to go through and do whatever it is I ask. That's the load. That's the resistance. That's the impedance of the circuit. So how much work does this thing have to do before it gets to ground, or how much load are you putting on it? That's what's going to set actual power. And I want to show that to you using a very simple calculator for something called Ohm's law. So Ohm's law is something that states that the amount of power that you get is going to be based on a function of the voltage that you put into the circuit and the resistance of the circuit. And it's very easy to determine any one of these if you have something up here. So watch, I'm going to try to show you what's going on over here using this basic Ohm's law calculator that I found on the internet through Googling. So we're going to clear this. So let's say I have 12 volts, right? And let's say the circuit of the resistance of the circuit is 5 ohms. I will get 2.4 amps. I can't change amps over here. Like if I try to change amps, it'll give me an error, because I can't have this amperage with this voltage and this resistance. Let's watch this. You can figure out pretty much anything in the circuit from having 2 of these. So let's say if my voltage is 12 and my current is 5, that must mean that the resistance is 2.4 and that my power is 60 watts. So this is something, by the way, that is useful to a lot of people who are troubleshooting CPU vCore circuits. So something that I see on a lot of forums very commonly is, my CPU vCore is shorted to ground. It's not working. It's shorted to ground. And no, it's not shorted to ground just because your multimeter beeps. You probably have a multimeter that beeps anytime it sees 1 or 2 or 3 ohms. It just starts beeping. It thinks that that's a dead short. So here's where using your brain comes in a little bit. So we know that most of the time, let's say CPU vCore, which is the power the CPU runs off of, we know that that's 1.05 volts, right? Now, keep that in mind here. Now, we also know that a lot of these CPUs, even the really efficient ones, are using about 18 watts. So a lot of these little, Ultrabook CPUs, when they're at full load, use 18 watts of power. So we have 18 watts of power, and we know that the voltage is 1.05 volts, which means the resistance on that line is 0.06 ohms, which your multimeter will read as a short. So again, this is how, if you have a little bit of electronics knowledge, you can figure out that, the CPU is just a really low load. My CPU vCore is not shorted to ground. That is not my problem, and and that's it. This is some of the stuff to think about here. So for any given voltage. So for any given voltage and resistance, you will get a certain amount of current. So let's say the MacBook works off of 12 volts. And let's say it's using only 20 watts right now. You can actually figure out how much current it's using and also the resistance of the circuit. If it's using 40 watts, you can just delete these two, and you can figure out the amount of currents being used and also the resistance of the circuit. The resistance of the circuit, or the impedance, is always going to have to go down if you want the power to go up. Another example of voltage versus current here. Let's go over amplifiers. This is a common misconception that a lot of people have. For example, a lot of people say that my speakers are a difficult load on an amplifier because they're about 3 ohms. So this is the amplifier that I have here. It's a Parasound HCA1000A, and here's the thing. It's not that they're a more difficult load. It's actually a simpler load. It's less of a load altogether. They're 3 ohms instead of the average speakers, which are 8 ohms. So this over here says that my amplifier can put out 125 watts per channel into an 8 ohm load, but that into a 4 ohm load it can put 200 watts of power. It is an easier load. It's not a more difficult load. It is actually an easier load. Why is it that the amplifier is able to put out more watts into a lower impedance? Now, for any given voltage, if you lower the resistance or you lower the impedance, when you lower the resistance and the impedance, you get more power. So this can actually put out more power into these speakers than it can into others. Now, the reason it's called a more difficult load is because with that garbage that you buy in Best Buy from Onco and Yamaha and all those systems where it's like you get 5 channels at 100 watts a channel for like $200, where it's bullshit, when you plug it in, when the resistance goes that low, the system does not have the capability to deliver that level of current, so it just turns itself off. The speakers are actually an easier load, but the amplifier itself is such a piece of shit that it's not able to deliver that power through to it. So keep in mind that you cannot set current. You don't set current. What you set is the complexity of the circuit and the voltage, and that's how you get power. Now, depending on what the circuit is doing, its impedance, resistance, however you want to phrase it, may drop or may go up, and that's going to set the power usage. But at any given voltage, the current that's going through it is not something that you can set. You set that by changing the resistance of the circuit. You can change the voltage of the circuit, and you can change what's in the circuit, but you can't set how much. You just can't say, I want more amperage to go through the circuit. You can't. The only way to send more amperage to the circuit is to up the voltage or lower the resistance. And that's how voltage and current works. That's the difference between them, and hopefully this makes some sense to you. So again, if you think of it with my silly analogy, hopefully my silly analogy makes understanding voltage versus current a little bit easier than this whole Joules, Coulombs, V equals J over Q nonsense that they're talking about here. Again, that's very important if you're an engineer. That's very important if you want to get a formal education. But if you just want to have an idea of what voltage and current is, it's just a little bit confusing. So think of it like that. And hopefully that makes it a little simpler.